Let me share the screen. First, we have to cover our regression part. First, we have to complete our regression part. So let's begin from here. Okay. So yesterday we took some equations to understand how exactly the linear regression works. For simple linear regression, what is the equation and what does actually it means? And so does we have also taken it for the for our multiple linear regression as well. Now that we know about these two equations, mathematically how these linear regression is actually represented, let us try to understand in much more better way that how exactly this linear regression works and what is the expectation from it. Equations and all are fine, but how exactly it works or what are we trying to gain from this linear regression? That's what we try to solve it next. So all eyes on the screen. Let's get started with our today's agenda with linear regression. Okay. Goal of linear regression model. Let us establish a relationship between dependent variable y and independent variable, one or more independent variable x, such that our LR model can be used to make prediction for unseen or new sample, new not sample but new features, sorry. Already explained you what is the meaning of feature and what is the meaning of your label, correct? So it is continuation of the yesterday's part only. Let us imagine that this is our x and y. That same thing, y was revenue generated from number of clicks on website in a business week. Let us imagine, let us consider here my different samples here. I'll take my sample distributions. These are all my sample distribution part. Now, point is that we are not looking to just create any line here, but we are trying to create here a line which is called as best fit line. Otherwise, we are having possibility number one. This is one possibility. Okay, the other possibility that we can pick here out of all this is we can just take different colors here to differentiate. Oh. Let's say this is one second possibility. Then we can have third possibility. This is your second. Then here comes your third one. And then comes my fourth one. Now just look at around all these different options and find the best fit. Which is best fit out of all? That's my question. The linear regression, basically what it does is it takes all the data, to find out one simple answer. And that answer for which one is best fit? Option number 1, 2, 3, 4 or 5. How does it choose that which one is best one? Answer is pretty straightforward. We are looking for trying to fit, we are trying to fit all our sample in such a way that it will cover the maximum points should lie on this, the maximum values should lie over it, and apart from that, the maximum samples lie over it, and apart from that, there is one more thing that we have to consider, and that is the if any sample is deviated, all your samples should be as closer as possible to our predicted surface or predicted line. So in this case, you can see these are the possibilities. That means we have to look for a point which will be having less error. Correct? We are looking to have a least value of the error. The overall error should be minimum. That should be the best fit line. That should be the criteria to choose the best fit line. Okay? By looking into this, currently it looks like that 3 is the best fit. Why I am saying 3 is the best fit? Because you can see most of your sample is falling near to your black line. And that is our goal. When I say goal of linear regression model is to find the best fit out of all the possibilities. Infinite possibilities will be there. And that is what the linear regression try to find out. It looks for all the samples, then it trains for it, and then it finally finds a best fit outcome. And when you say best fit, it clearly indicates that your all the samples should be either falling on the line or it should be closer to the line. I'll repeat again. Either all the samples should be closer to the point, should be closer to the regression line, or should be closer to the falling over the regression line. Sorry, regression line, correct. So that's what the main purpose is. There could be many possibilities. Find the best fit. Best fit means best train. Fit means train only. Okay. So in order to find the best, we have to look for the residuals. Residual means nothing but it is your error value. And let's get started. Imagine these are my sample distribution, few of them falling over the line, few of them are obviously distributed across this. Now let's try to look for these points here. This is your first point. Find the perpendicular value. It will fall over this. We can call this as y1 hat. This particular value will be y1. And second value will be y2. y2 hat. Next goes with my y3. y3 hat. y4 hat. Remember, wherever I'm writing hat, it means it is a predicted value and that will fall over the surface. y5 hat, y5. y6 hat, and I think we can settle down for these many points, okay? Imagine these are all have fallen over the surface. So, wherever there is a difference between actual value and the predicted value, what does it call? It is called as nothing but it is called as your residual error. E1, E2, E3, E4, E5 and E6. These are all your error terms. We can call it as residual error. We can call it as residual, which is given by sum of, this is your differences between y actual and y predicted. This is particularly called as your residual. Okay, residual or error, because both mean the same thing. So let's try to figure out. If I have to calculate it, I can just simply take here y equals to y1 minus y1 hat sum y2 minus y2 hat y3 minus y3 hat and yn minus yn hat. So for all these samples, we are trying to take their differences. We are trying to find their differences between actual value and the predicted value. Now the question arises, can we just write the error value as this? Can we find that my error value, the total sum of the error will be equals to yi minus yi hat we take the square, yi minus yi hat, can we take this for all these samples? This is the point. The answer is no. We cannot do this. Why we cannot take? Because we have to, because there will be a problem here. What is the problem? Sometimes you can see that your error value will be positive, the other time you can see that it is negative. Is that part clear? Error E1 will be positive, y1 minus y1 hat, but on the other time you can see that your y3 minus y3 hat will be negative. Okay, so there's a clear-cut indication that your total sum of the error cannot be calculated by simple summation. And the reason is your error could be positive and error could be negative, rejected because difference between actual and predicted can be either positive or negative. Either positive or negative. So, in order to get rid of this, when we will total sum them, we will not get this point. So, what will be my error? The sum of error equation will be given by E equals to 1 by n sum of y minus y1 hat, and we take a square of it. yi minus yi hat, and we take the square. This is your total sum of error with an average value, and it is divided by n, called as your mean squared error. MSE, mean squared error. The equation is called as mean squared error. This is your error equation for the regression part, and ultimately we have to look to minimize this part. By the training process, we have to minimize it. Okay. Any question in this residual section? So we are trying to find out this error, and we have to settle down. We have to minimize it. I mean, not we, but obviously the linear regression model will try to minimize it. That's what the main purpose of all these regression model is. It will try to minimize so that our overall value, our regression model should become a best fit model. From unfitted model, it will be settled down for a best fit model by the help of all this. That's what your residual is. That's what the purpose of this finding the residual part was. You have to find it. N is your total number of samples. Here N is total number of samples. N is your total number of samples. Okay, these are your samples here. There will be many samples for which the error value will be 0. Yes, it will be vertical projection. Your actual values, vertical projection will be there over the surface, and wherever it is projected, that will be called as your predicted value. This will be actual, and this will be predicted. Wherever hat is written, it means predicted. Okay, and this line will be called as your regression line. Now, from a normal line, we have to convert them into a regression line by simply fitting it and when we try to fit it, we are trying to simply reduce the error, okay, and then we can apply your regression model here straightforward, okay. Now I think this is more than enough. What we have to discuss here is that how does we can apply this regression model technique, and we can minimize it, okay. Fine. Now let's go for and find the attributes here, trying to find out y equals to in this equation. Now remember that how does we can reduce the error? That answer is still not been given. How to minimize the error? The answer lies in this equation. Let's try to expand this equation. Error is equals to 1 by n summation, and now expand this equation. Yi, that is my actual value, will remain as it is. What is my predicted value? Predicted value is actually calculated by this beta naught plus beta 1 into xi, isn't it? Yi is nothing but it is your actual, and this is my predicted. So my error, from this we have to find the error and then we have to minimize the differences. Now think about how we can reduce the differences. How to reduce the difference between actual and predicted. Yes, think about it. If there is any error, that error will be probably because of the differences between these, correct? Yes, that's correct. If you will look at here, you will see that these values will be wrong, because that is your predicted value, correct? So that's why you can see here in the equation, I'll take the help of your PPT's part to explain you this further. So if you will look at here, your y actual will be given by this particular equation, which is nothing but it is your y hat portion plus mu. This is your residual or your error term. So y hat plus error, and that gives you the y actual, or you can do the reverse of it, difference between actual and the predicted value, and we have to minimize this particular value. Okay. So approaches that we have to, now if you will expand this equation, beta naught is nothing but it is your intercept value, whereas beta 1 is nothing but it is in this equation will be given by slope, that is dy by, this is your differentiation, partial differentiation of dy by dx. Okay, and then we have to find out the residual. Residual is calculated already, I given you the residual part. Slope is dy by dx. Intercept is your initial value, and we have to adjust all these points. Okay, how does we can adjust all these points? By changing the slope, by changing the intercept value. These things has to be adjusted as per our samples. We have to change these values and we have to convert them into fitted part by modifying beta naught and by modifying the beta 1. You can see this, right? If your beta naught will be changed, so your angle will be also reduced. You can have this as one of the option. This could be one possibility. This could be another possibility, right? So when you will change the slope, we have to settle down for them, for which our overall sum of error or overall residuals will be minima. Fine. Hopefully now you have got it. How the linear regression is gonna be working. Anybody having any questions, please ask it in the chat. Also remember that clear from all this. Just asking for a question. Just asking one question here out of curiosity. That what happens if I try to pick here? Okay. These are all your different sum of a squares. Sum of a square is nothing but it is about your error part. This process is called as least square approach. This entire process which I am trying to say was known as least square approach. When you try to minimize the value, each and every individual value, by adjusting the slope and by adjusting your I'll come back to this part a bit later. Somebody has asked me about related to what if we will be having more than one independent variable. Same rule will be applied. In that case, the equation will look like this. 1 by n. Summation will remain as it is. Yi minus beta naught plus beta 1 into x1, beta 2 into x2, and we take the square of it. Okay. Now in this case, what will happen? We have to adjust what? The parameters beta naught, beta 1, which will be given by del E by partial differentiation of error and partial differentiation of del beta 1. Similarly, we can take here del beta 2 sorry, trying to write here is this one, del E by del beta 1 will be there, but this time beta 1 will be not your slope, but it will be coefficient. This will remain intercept, and these two will be called as your coefficient value. Okay, and we have to adjust them. We have to again adjust these coefficient of say x1 and x2. So rule remains same. There is no change here. Moreover, just wanted to convey one more thing. Suppose in case your del beta naught is 0, beta naught becomes 0, then in that case your y, okay, beta naught will be 0. This will only happen when your y is equals to x. There will be only one scenario. That means in this case you will get this type of line, this type of regression line. Okay. Now here in this part, your y bar Let's try to find out these equations, these terms here, called as sum of a square. SSR is sum of a square, sum of a squares for your regression. This is your sum of a square, error of the sum of a square. No, I said beta naught. When beta naught will be 0, then you will have a scenario of x equals to y. This is x equals to y equals to 0. If both will be 0, then no line will be created. There will be no more of a regression line will be there. Obviously, x equals to 0 will be what? Y-axis, and y equals to 0 means what? X-axis. Correct. So that is not a regression line. That will be like meaning that all these points are falling over this. Anyway, let's take our last part and then we can go into our example. We can do by the gradient descent or we can do it by least square approach. In this case, we will be applying least square approach. Both methods are used. Gradient descent could be also the one of the methods, or you can apply the least square method. The technique, the equation that we write here, right? The equation that we write, in that most what we do is we now let's see the different equations here. Sum of a square, regression, and a sum of a square error as calculated. These are your two different points. First of all, this denotes your mean. This is your mean line, the average line. Okay, this is your average line. Next is sum of a square. Find out. That's your difference between your SSR is what? SSR is nothing but it is your difference between actual value. Imagine that here is your actual value, this is your actual, and this is your predicted line. Sorry. Here is your actual value, and this will be your predicted line. Right? We have to take a straight away vertical line over the regression line, or called as your least square line in this case, as we are applying the least square approach. So y actual, we are trying to find out here y actual and my y hat. This is called as SSE. This is called as sum of a squares error. Difference between actual and predicted. Just now we discussed it. This is nothing but this is your error term, right? So we have taken that square value. The difference is that we are not taking the mean, so we cannot call it as MSE. What we have to take here is the actual versus predicted. So this is the same thing, y actual and y predicted. And we all know why we have to take the square, so that we can eliminate the negative sign. What is this called? Y actual minus y hat. Error value Because we have taken square of it, that's why it is called as sum of a square. That's why it is called as sum of a square error. Next. Next part is the mean and the difference between mean and your predicted value. Mean and the predicted value is calculated by, this is your predicted line, sorry, predicted value, and this is your mean. And we take the square of it, this is particularly called as your sum of a square regression. When we calculate the differences between actual and the predicted line, it is called as SSR, sum of a square regression. Fine. So let's try to understand in another term that SSR or the regression of the sum of a square indicates the difference between regression line and the mean of the response of the variable. This is the variability which is explained by the model. This is nothing but this is your variance or variability. This is your variability or variance from all the average point. This is your average. So how does you can particularly measure that what will be the variability? Variability is always measured from the mean, right? You talk about the variance equation. What we calculate in the variance? We calculate that how much your current value, the predicted value is deviated from the mean value, correct? Similar type of thing we are trying to calculate here as well. This is your mean and this is your predicted value. So when you try to calculate the difference between your mean and your predicted response, this is called as your variability. Fine, first part is done. This is done. SSR is clear that why we need it. This is going to tell us the variance from the mean value. Once we have got this could be again, it could be positive or negative depending upon the placement of your y-hat. Like for this particular point, your y-hat will be lower than this, correct? So it could be negative or it could be positive. Moving to the SSE part, which I have already explained. SSE is your total sum of a square error. This indicates the difference between your observed value and the regression line. This is the case where the amount of variability is explained by the model. Okay, now these are some of the terms. If you wish, you can keep it in mind. SSE is variability by model. Variability explained by model. The regression model that we have created. Fine. So now if you will just look at here, so smaller the value of your SSR or SSE, the more accurate the prediction will be. This will make your model a better model. So these will be your criteria to particularly measure that your model is good or not. SSE and SSR are your two criteria to choose if your the model performance is, that if your model performance is good or bad. There is one more term that we can discuss here, and that will be R squared. Coefficient of determination. Coefficient of determination. This is your overall performance of the variability part, right? When it comes to measuring the variability explained by the model. So this is the proportion of the variance in the dependent variable that is predictable from the independent variable. the proportion of the variance in the dependent variable that is predictable from independent variable. So R square will be given by 1 minus SSR upon SST. Simple it is. It is given by your we are trying to find out here the total variance explained by model upon your total variance. SST is combination of SSE and SSR. SST is SSR plus SSE. Okay, done. So R squared will be giving you a score, a value that will be the main criteria to choose if your model performance is good or not. Fine. So just keep this equation in your mind. I mean, mathematically it is not important to understand, but what exactly this explains is important here. That it is going to give you the actual idea that how good your model is fitted, and the range of the R square will be between 0 to 1. The more it is closer to 1, that means the better is your regression model. That means in that case, the difference will be least. And if this particular value is closer to 0, that means the model performance is not that great. Okay, clear? Give me some time. You all can post your questions for a minute, and then we'll start with the practical. Can you explain one more time how do we calculate coefficients? What is the meaning of calculating the coefficient here? We are trying to adjust the coefficient here. Calculating the coefficient, I am not understanding that point. Please explain more. We are trying to adjust the coefficients, not to calculate the coefficients. Yes, RMSE is the square root of MSE, that's correct. For the time being, we can settle down for MSE part. And when you take the square root of this, that gives you the MSE part, sorry, RMSE value. This is your MSE equation. Just now I explained you R square value, coefficient of determination. We calculated by putting up this part, R square 1 minus SSR upon SST, which indicates your total variance explained by the model upon total variance. Total variance is your SST. And SST minus SSR gives you SSE. Might be indicating that this is your total variance explained by the model. And SST will be your total variance, which will be combination of SSR plus SSE. And this particular value should be the measure of that if my value is actual or predicted. How much your overall performance of the model is closer to your predicted value. Okay. So this should be range between 0 to 1, and we have to look for a value as much as closer to the 1 value. If the higher will be the R square value, that means the more it is closer to 1, the better will be your model performance. Clear? Uday Kiran? Okay, so that's it. This is all about it. Now, here we are trying to approach a least square method where we have to particularly find the slope. We'll calculate the slope, we will calculate the coefficient, and we'll try to adjust our overall error. This approach is called as by the mean, by the average value. This approach is called as least square. There is one more approach which you might have studied in somewhere in book, and that approach is called as by using gradient descent. So that is also there. Here we don't need it. This your equation which is available to us is going to be the least square part, and we are trying to apply our least square approach. Sorry. So shall we get started now? This is it. And yes, we have to, why we apply least square is, one of the reason is that it is fast. Okay, let's get started with our coding part. We can take here one example. So I'll take one example here and let's try to adjust them. This is from your practice example. So number 8, right? Okay, so from the lesson number 8, I'm going to take one project here for your machine learning, and let's take one example out of this. You can download the dataset from the, okay, I think many of you have updated it as well, so maybe your dataset will be also updated. Wait a second, I'll upload it in the GitHub and then I'll share you the link. We're going to take simple example for finding the an Excel sheet is there for advertisement or advertising budget and sales. That's the data set I'm going to take. So I'm just keep providing you that CSV file. Please open the example. Sorry, please open your code here, the Jupyter notebook. Here is your raw link that you can use. So you can see your data set. It is pretty straightforward data set. First example should be simple always. TV ad budget, radio ad budget, newspaper ad budget, and sales. You can compare one-on-one or you can compare all versus one. These three versus one. So what is the impact of TV ad budget, radio ad budget, newspaper ad budget over the sales? If you wanted to measure that, the only way through which we can do it is your, so how much you allocate these budget, what is the overall what is the particular thing that it indicates when it comes to your overall performance of the model. So let's get started. This is how your question actually looks like. This is your assignment. So assignment is to evaluate the ad budget data set of XYZ firm who have allocated these particular budget values. Okay, so let's get started with first. Now the steps part, hopefully you all remember it. Yesterday only we discussed. MSE should be lower always. MSE is an error, so obviously minimize lower the minima, lower the error and better it is. Don't worry, now in a minute you will able to know all these points. Where is that flow chart? Yeah, here it is. This is your machine learning approach, isn't it? So we have to follow the stages, these different steps, and let's try to find out the working of supervised learning model. We know the data, we see our observation, we find our features and responses, and then we split the data, then we provide this into our model, the machine learning algorithms, measure it, and then we have to make new predictions as well. So let's get started. First, we have to import our data set. So I'll rather be preferring to write in a different one. Let's get started. Import data set will be your first step. Point number 1, import the data set. Now you don't have to save save the data set that I provided you. Just like the way we did earlier. It is similar to how that we used in our Jupyter notebook. So either you provide this entire URL or you save it and then take the path, local path. This is up to you. Let's import our libraries which will be helping us. Import NumPy as NP. Import Pandas as PD. Import Matplot, lib.pyplot as PLT, and import Seaborn as SNS. Okay, start working. I'm sending the code in the chat. Now everybody, please change your send to option 2, host and presenter, so that I can see your questions, and others will not able to do so, and this will not affect the coding part. It will remain good in the chat, unaffected from your options. Okay, so first option is import the library. Then we have to import our advertisement data. Now those who are worried about how to choose the data set, here is your URL link. You can use it straightforward, or if you wanted to save it on your local machine by using right click save as, you can save this file and you can start using it. So it is up to you. I'll just simply save it in my e-data, wherever my all data set lies. I'll just save it there. If you wanted to take it from the URL, so I'm just giving you that link so that those who don't know how to save, you can straight away get rid of all the issues. So df underscore advertisement data underscore df, this is equals to pd dot read underscore csv. We take a path. All the participants, please change your send to option. Okay, so that's your value here. You can see all these are my data set. So either you use this, let us eliminate the first row. Let us eliminate the first row here, sorry, one column. So this particular value I wanted to replace. In fact, I wanted to make it as my indexes. So that's the reason why I've written here index column equals to 0. That is, my first column becomes my index values. So in spite of having the indexes 0 to 1, we are having 1 to 200. I'm just sending the code now. Separated by comma is always optional. Default value is always comma, so it is not always important. The next line says that display view the initial few records of the data set. So let us eliminate it. Let us try to eliminate this part. This is part of your one of the assignment in your chapter number 8. So next is your analyze the data set. First part is view the initial few records, which will be used for advertisement data frame. Use here head. These are all your records, looks good. Check the total number of elements in the data set. This could be easily checked by our advertisement data frame part. Dot shape 200 rows, 400 column, or you can write here size. Total number of view the data set. Sorry, check the number of elements in the data set. Correct. So you can just find out here the shape, which will be indicating 200 rows. First read the data, shape, head, start working. Next could be okay, number of elements will be, I think, more of size type. Sorry, make a correction here. This will be total number of data. So size will be better. Please update this total number of elements by size. Find the features or media channels used by the firm. Part number 3. Okay. I'll wait for your confirmations. Once you reach us till here, then tell me. I'll go with our next part. So till here we have discussed just a few initial things. If you are done, just drop done in the chat. If you are done, just drop done in the chat. Everybody drop done in the chat if you have finished till here, if you have done till here. Okay, great. Now let's find out the features. Find out the number of rows and number of columns here. Check the number of observations, that is number of rows and number of columns. You can easily figure out it by advertisement data frame, dot shape. 200 rows and 4 columns. View the number of each of the attributes. Attribute means your columns. Data frame name, dot columns. These are some of the initial things which we have to always do. Part number 3. First and second. Display the data set. All these values are there. Here are your different column names. TV and budget in dollar. TV budget, TV ad budget, radio ad budget, newspaper ad budget, and sales. Now, out of this, we have to find out our x and y value. We have to find out our x and y value. So next part is my create our objects to train and test the model and find the sales figure. I have given the same data set. This was the data set which I provided initially. The same data I am also using. Maybe you can just refresh and restart. Sorry, you can just do kernel, restart and run all. There was just 200 rows in this, so there is no possibility of 1000. The possibility will be only 800. Now, as we have finished our objects part, create object to train and test the model and find the sales figure for each channel. Before we reach here, we have to basically create a feature object. Before we jump into this part, I like to add some additional stuff. So whenever you do any regression part, regression example, you have to take here our values. Now wait for it. In this case, we have to do some regression examples. So before we jump into this splitting the data part, let us try to understand some more concepts here. Linear regression is having some assumptions here. Okay, also we didn't check out for the missing values and all. So let's talk about some of the data manipulation part and assumptions. Assumptions I said right. Assumptions of LR model. First of all, our data should be neat and clean. Yes, in this case, there will be no error, but it is important that we should check it. So we have to check for if any missing values are there or not. First part will be handling the missing value. We have to find here if we have got any missing values in our data set by using symbol is null dot sum. So you see that all four columns are 0, 0. It is important to check and monitor if all values are displaying zeros or not. If it is not 0, then we have to handle them, which I'll take in our next example. For the classification part, I'll choose a data set which will be having certain missing values. Okay, assumptions. In the assumption, we have talked about probability distribution, right? That PDF function. So remember that your probability distribution of target column, in this case my target column is sales. So of target column must be normal. In other terms, sales must be normally distributed. Sale must be normally distributed. This is our assumption. If it will be not a normally distributed data, we have to make it one. This is our assumption part. Assumption number 1. So let's pick my column. Dot. Sales dollar. And we have to pick this and we have to put them in distributed, our plot part. So simple, you can take SNS.distplot. Don't expect that. Here is my data set. Shows more of a normally distributed part, which is good. We can take here all my values here. Figure size and all. This will show some normally distributed pattern. And the value looks like a little bigger. We can adjust the size. Okay. Right. Now that is one thing. Suppose I wanted to compare if it is actually normally distributed then or not. So you just write here fit equals to norm. Norm function, norm is particularly is a package which comes out from SciPy. So pick here from SciPy dot stats import norm. This will be showing you the trend of normally distributed versus your actual distribution. No, the reason is simple that we want in machine learning we always try to create a model which is general model. We don't create a biased model. So if your data is normally distributed data, it means that it does not have its bias value is 0. So that's the reason why we have to ensure that our data is normally distributed data. By the way, this is your one core assumption. This is your one core assumption part. Okay. To disable these warnings, we have a package which you can use, import warnings. These warnings will always disturb you. I mean, warnings dot, or what we write, this is from Python. Warnings dot filter warning, just write here, error. Warning dot filter warning, just write here. Just write here, sorry, error will be not there. We have to write ignore. Done. So black line indicates your actual normal distribution case, and the sale is your other distribution part. Okay, now if you don't like this color, you can definitely change it. I'll go for dark violet. Okay, so here we go. I'm sending, don't worry. This is your assumption part. So remember that we have to always check if your data is normally distributed data. So there will be no ideal case scenario, but if you see this looks like more of closer to your black line. So yes, our data is having a sign of normally distributed data, which is a good thing. And here, if the more it will be closer to your normally distributed data, the better will be your prediction for this. So these are some of the key aspects you have to always look for it. By the way, there was one more plot. Anybody remember? I talked about it in our plot section, that how to check if your data is normally distributed data or not. There was one more plot, I discussed it. Quantile plot, QQ plot. Not box plot, no. QQ plot was there. Remember that red line? Okay, sorry. For your batch, it was not important, correct. But distribution plot is fine. This one is done. Okay, guys, already shared the code. So please check your chat, scroll up, and find your code and start working. That's the end of your important section here. It is done. Now that we know about this, if you wanted to do one more part here, some side of a hypothesis testing, wanted to do it here with a correlation. Let's try to check which out of all these features are best. Remember, these important details will remain common, whether you are solving it for this particular problem or for any other coming problem statement. The flow will remain as it is. You have to always test for your normal distribution. So as I was saying, that if you wanted to test, there is one more plot which is called as QQ plot, quantile plot. Quantile, or rather I'll just simply write here QQ plot, which is used for checking if your data is normally distributed. I'll simply straightforward use our data set and I'll make a plot here. This is also coming up from stats, SciPy. SciPy, all your stats part is always part of your SciPy thing. Okay, so that's this is your first part. Then second part is about QQ plot. Let's try to check it here. Res result equals to stats dot probability plot. Okay, probability plot. And why it is called as probability plot? Because obviously this is nothing but it is your probability distribution. Okay, that's why probability plot. That's the name. Boston. Sorry, what is our data frame name? Oh God, I went to some other data set automatically. Advertisement, right? Advertisement data set. So pick your target column, which is sales. You can straightforward copy and paste this. And then pick here your plot equals to PLT. This is nicely settled down and it shows clear-cut indication that your data is normally distributed data. How does we have to measure it? Pay attention. You have to just see the plot and you have to check that how closer the points are to your red line. This red line is your normal line, and the more these points will be closer to your red line, that means the more normally distributed your data is, then more normally your sales data is. Fine. So that's how you can check it if your data is normally distributed or not. This is the best way to check, actually better from this. The more sample will be closer to your red line, that's how simple you will check that if your data is normally distributed or not. So these blue dots are your sample dots, and this is this is your theoretical quantile and your ordered quantile. That's why it is called as quantile plot. Our indication is just one thing, that we have to ensure our value is falling over the red line. If it is falling over the red line, just say that it is a normally distributed data. Going for the hypothesis testing for correlation, let's find which particular value is highly correlated and which particular value is not. So just like the way we created our SNS.heatmap, I'll take this value and I'll put a correlation function. And let's find out our correlation value. Again, same, A0 equals to true. Color map equals to, you can choose any color here, or by default let it be. Okay, sales versus sales has got a very high correlation. Sales is a highly correlated value and it is highly correlated with TV and budget. With radio and ad budget, with radio ad budget, it is coming out of a 0.58, and with your newspaper ad budget, it is 0.23. Quite a good correlated values are there. If your data is not normally distributed data, then you can convert them into normally distributed data by pre-processing, by the help of standard scaler or by the help of min-max scaler. We have to do that. I'll show you in this part as well, even if our features are not normally distributed, right? So we will do that. That is simple. Standard scaling could be done by standard scaler using sklearn package, or we can do it with the help of our min-max scaler. Okay, anyway, our data is done. This is all our data. This is how my data looks like. Now, after going through all these checks, this step could be used for feature selection. The weaker correlated value you can ignore, or you can eliminate it before you proceed for the step number 4. Okay. So I'll wait for your confirmations. If you are done, then you can just tell me in the chat. Quite a simple and easy one. After you have studied all your stats, no, machine learning is quite simple. But if you don't know those basic fundamentals, This question I have already answered 3 times. Please pay attention when your data is not normally distributed data. Now again, everybody is asking the same question. Just now I answered it. If your data is not normally distributed data, then using sklearn package, there are 2 methods. One is called as min-max scaler, and the second method was standard scaler. So either we standard scaler it or we do the min-max scaler. These are your 2 steps to convert your data into normally distributed data. Both will be doing your work if your data is not, in case if it is not normally distributed data. These are your package and this is part of pre-processing, and I also said additionally that I will be showing it how to do it for features, because anyhow features will be not normally distributed, so we have to make them. Okay, done till here. Coding part completed. Everybody's coding part is completed. Please drop done in the chat. Now that we have created all this, let's discuss. The plot is same as it is. There is no change in the plot. All the participants are requested to change your send to option to host and presenter so that the coding part is not getting affected here then. Okay, let's next part is create a feature object from the columns. Create a feature object from the columns. So let's get started with that. In order to see our features part, we have to pick your X value, create your X feature. X feature equals to your advertisement data. Either you can do it with the help of colon 3, colon comma 3, or using log part, or the other part is I can straight away do the thing simple. I can select my column by column names. I can select it by my column names. So these 3 columns are there. I can simply copy paste and I'll put them in the list. Create a feature object from the columns. Next is my target value. Next is my, so view the feature object. In order to view the feature object, you have to pick your X feature and you have to show it with the help of head. Next part we have to discuss here about is after we have taken our features, we have to take our target. So features and target are two points. And let's pick my target value. What will be target here in this case? Participants, what is the target in this case? Sales will be the target, correct? So we are trying to make predictions for the sales, and that predicted value will be always about the target column. So we pick here my target. Advertisement data frame. We have to pick here my sales column. Sorry, sales in dollar, right? Sales key not found, obviously. So sales is my second column here. Got here my target value. We display the target. Now let me send it all these points on the chat. First we selected our, we took our features. Then we chosen our target. Select your features and target. Right, so this is how our values will be selected. Now remember guys, your main feature selections criteria will be on the basis of correlation, especially for the linear regression part, because as I have discussed in the theoretical part as well, that correlation is a measure of linearity. So that's how, and your linear regression is obviously trying to establish a linear relationship between your sales and your features. Now in this case, we already know that our target is going to be sales part. Rest all becomes my feature. What is my feature in this case? TV ad budget, radio ad budget, and newspaper ad budget. These are all my three feature number one, feature number two, and feature number three. If any value shows me a weaker correlation with respect to sales, that particular feature will be dropped. Is there any value out of all three is closer to zero? The answer is no. None of these are closer to zero. If no value is closer to zero, that means all three features, all three TV ad budget, radio ad budget, and newspaper ad budget will be affecting our sales value. That means these are all my three good features. So with no need to drop any other features here, we have to go for TV ad budget, radio ad budget, and newspaper ad budget. Okay. Who are, what is the name? It's BS. I think, buddy, you have to go for our previous sessions where I discussed this linear regression thing in past week. I think you have forgotten that part, so it will be easy for you. Is there a threshold below which we consider a feature or not to be strongly correlated? Yeah, for the stronger one, we do have a threshold 0.85. That is how I select. This is not subjective, but it has to be 0.8 or 0.85, closer to it. This is a good question, by the way. So see here. If for the higher correlation, strongly correlated, you have to look for. So weaker correlation it is quite simple. As you know that correlation is a range between, what is the range of correlation? 0 to 1. So the zero value will be obviously closer to zero. You will see zero value 0.00 something like that, like 0.055, 0.057. So that's okay. But what about the higher value? That is more important because there could be a scenario where you can get a very high correlated value. So the threshold value you can keep it as 0.8 or 0.85 depending upon your data requirement. This is not, totally you have to follow it. Strictly you don't have to follow. You have to look for what is coming out to be good for you. Sometimes 0.75 could also come out to be good. So any range 0.85 to 0, sorry 0.85 to 0.75 to 0.85. Beyond this, if any value crosses, that means it is highly correlated, and that is also not good. In fact, I'll settle down for 0.8 to 0.85. So anything which is greater than this range, that is also not good. It means that there is a huge dependency over a certain feature. It is almost like a scenario of y equals to x. Okay. So we don't create such model. We create always, we assume that all features are having equal contribution in change of the y. If there will be one feature which will be strongly correlated than other features, then it will become a biased model towards that feature. It will be more of a scenario of, you think of it like, what is correlation? It is nothing but it is showing you what is the relationship between your y and x. In this case, my y is sales. So between sales and TV budget, if it is come out to be 0.88, it means that automatically your radio budget and newspaper ad budget becomes irrelevant. All your sales is dependent on TV ad budget. That will be the meaning of that part. So just take this into the consideration that it is higher threshold value is important, and that's what you have to consider. This you can just add it somewhere in the comment or somewhere in your note. And for weaker, we already know that it should be closer to zero. All right. Next part is view the feature shapes here. We have taken the target, we have viewed the target, verify if all the observation has been captured in the feature object. This is particularly about the shapes. So x underscore feature dot shape got 200 cross 3. Similarly, we have to verify if all observations we have to capture. So for this, you will simply write y target dot shape. Got here all my values, the x feature and the y target. Okay, so it verifies that all my data is done. After this, our next step is about splitting the data. That means we have to split the data into training and testing model. So split the data set by default 70 is to 30 is saying 75 25. So we can follow that. Otherwise, you can have any range, right? Between 70 to 80%, you can take any range of the data. Even 60 to 80, that's the range we have discussed in the theory part. So let's split the data randomly. Now this will be done by sklearn package. This will be done by sklearn package. So from sklearn, scikit-learn dot cross underscore validation. Sorry, model selection will be there. From sklearn dot model selection import train underscore test underscore split. Now this will return me four things: xtrain, xtest, ytrain, ytest. Take here my train underscore test underscore split. Take here my x feature. Y target. Apart from this, we can also take my value. We can pick here, pick my test size 0.25. We have to mention that, and we have to also write your random state. Random state, I'll talk about it a bit later. This part you can just ignore right now. What did we did here is we just chosen our x feature and your y target. We have taken our test size as 25%, so automatically your train size becomes 75%. And the data will be distributed among xtrain, xtest, ytrain and ytest. Let me provide you all this. After we have splitted all the data, now let's verify if the training and the testing data set that we have splitted are correct or not, and what is the distribution of them. So xtrain.shape, let's put all these values with print function. Xtrain.shape, xtest.shape, ytrain.shape, ytest.shape. Here are my distributions. 150 goes for the training, 50 goes for the testing. That's the distribution, 75:25. So split the data into train and test. The data is distributed here, and that's how it looks like. Please finish it till here. In 36 lines, we have splitted the data into 75:25 ratio. Your X feature got splitted into Xtrain and Xtest. Your Y target got splitted into Ytrain and Ytest. 75% goes into the training, 25 goes into the testing. So it's 75:25 ratio. There is nothing unusual. The range was 80 to 20, 60 to 80. I can choose any ratio. The ratio could be anything in this case. Random state I'll explain later. Are we done? Just drop done in the chat. Okay, great. So what did we do here is that we particularly try to take here all my data set. So this part is clear. We have splitted our data. Now we are following the same pattern as we discussed. The train could be anything between 60 to 80%. Test could be anything between 20 to 40. Correct? Depending upon how much percentage you choose. If you choose train here 20, this will be, sorry, 80, then test will be 80. If you choose here 75, this will be 25, and that's what we have taken. So we can take any values here. After we have taken, now it's time to create our model. After this step, you have to simply create a model. To create your model here, to create a regression model, all the other steps are ready. All we have to do is you have to simply pick your linear regression model. Create a linear regression model here. Let's get started from sklearn. From sklearn dot linear underscore model import linear regression. Pick here my linreg, which is equals to linear regression. Dinkar, what is the meaning of this pasting this part? So many times I said everybody to not to paste in the all participant side, right? Now the previous code will be get affected. Participant, this last part of the code is not from my side. Please take care of that. In fact, I'll just add the comment to ensure that this is was done. Please pick the code now from this. While taking the code, please check it is from my side or it is from Dinkar. Okay, participants, everybody is done. You have taken your data set. Okay, so the step includes first we have taken our linear regression model. We called it. So that's your model here. After you have imported the model, then you will simply fit it. Fit means train. This is your training of model, and when it comes to training of the model, you will only use your X train and Y train. Remember the size, the shape should be similar. That means this should be also 75% and this should be also 75% of your overall data, which has been equally taken here. Next part is print the intercept value, intercepts and coefficients. Print the intercept and coefficient value. In order to print the coefficients and intercepts, we can use simple linear regression. And we can write here intercept part. It shows 2.87. Linear regression dot coefficient value. And you see here, these are your coefficients value for your betas. Coefficients are nothing but these are your betas here, beta 1, beta 2, beta 3. Those are called as coefficients, right? Just remember this part. This is representing your coefficient value. Okay, coefficients, which are nothing but this is your beta 1, beta 2, and beta 3. Three betas will be there. So all these are your beta part. Put them around the print function here. Now remember here, the intercept denotes what? Intercept is your beta naught. Yes, it is correct, Uday Kiran. If you are not getting it like this, if you are getting it like, copy x equals to true, fit intercept equals to true, number of job none, and normalize equals to false, all are fine. Okay. Now you take all these values. Remember, this is your beta naught, this is your beta 1, this is your beta 2, and this is your beta 3. All these are your coefficients and intercept value. Now let's start making the predictions. So print your coefficients and intercepts. After printing it, we can make predictions here, and we can also display our metric part. Speed up, everybody. Time is about to get up, so we have to finish this before we go for our break. Already taken so many time here, just try to do it faster. We got here my intercept value. Now question arises, what was this random state? And what is the impact of this? See, random state is something which is like a seed number. Whenever you are generating a random sample, we use seed to fix that. So every time you will execute, you will get a same number. Similarly, random state equals to 1 indicates here that your distribution will be fixed. Your distribution will be random, but distribution will not change every time you will execute it. Imagine if you don't set your random number, or imagine that if you don't set your random state, then in this case, the point is, since you have taken here my random state value equals to 1, correct? So if this is my value, this is my random state, which will ensure that the data sample that goes into the train part and test part will always remain unchanged. Doesn't matter if you execute this code 100 times. If you don't write under random state, then the train and the test samples will be different. There is no effect of this in the distribution part. 75 and 25 will remain same. But the data which goes into the training and testing will be always changing if you will not fix your random state. If your random state is fixed, that means the number of the values which are going into the train and test will be also fixed. It will not change itself. Clear? No, there is no range for the random state. Generally, I prefer to take the number between 1 to 9 and then I monitor that for which particular random number I am getting a good accuracy. This do affect your accuracy part as well. So it's like a hit and trial part. You have to take a number, any number between 1 to 11. In fact, 0 to 11 you can take and choose which one is the best. Otherwise, this random state could be anything. Default number is 42. Default number from the scikit-learn is 42. But you can modify it, and the effect is clear to everybody that if you don't choose random state, a fixed value, then these value will be always affecting your result. So every time a new result, new model will be created, and it will be not a static model. It will be not a fixed model. Okay. Now that we have created our model, let's predict the outcome from the testing data set. Now let's predict the outcome from the testing data set. In order to make predictions, you'll choose your linear regression, and then you write here dot predict. In this, you will pass your X test, and these are all your predicted values. For your preference, you can place them in a variable called as y_pred. It will be much more easier for you to save your results, which is your ypred, and this is how your value will look like. Y predicted outcome, and these are all your predicted outcomes for the various features. So we have passed here features, and what we have got is sales. That's your all 25% of your overall distribution of the data. Okay, the next and the last part is calculate your mean squared error. Calculate your mean squared error. For the time being, I'll also calculate the R squared value as well, because R squared is important. Import the libraries for the MSE. So from sklearn dot matrix import, you will get here mean squared error. You can also take mean absolute, mean squared error. Mean squared error is there. So at the beginning, I have imported the NumPy part. Let's try to calculate here the mean squared error, and let's compare here the mean squared error with the Y test. So straight away you can write, okay, Y test and Y hat. This is your mean squared error. You can see how good it is. The value is just 1.9. So it's a very small value. You can also calculate your RMSE value. Remember that the calculation should be always for the RMSE part. For that, you can just do the np.sqrt, and that is the reason why I have imported NumPy at the beginning. You can place this mean squared error part here, and you'll get the RMSE, which is furthermore smaller, 1.404. You can simply import here 1.404. So you got your MSE, we have also got your RMSE value. There's one more thing additionally you can definitely try, and that is your R square score or R2 score. R2 score or R square value is your value that will fall between 0 to 1. The idea is that the more it will be closer to the 1, the less is the variability between the total sum of a square and your explained sum of a square. By the model, explained sum of a square versus total sum of a square, we are trying to compare. So less variability means high value of R2 score. Calculate that, we will simply import R2 score. We take here my R2 score, and we take here value between your Y test and Y pred. It's coming out to be 0.91. That's remarkable type of numbers. Never expect, don't expect that these type of numbers will appear. Okay, this is just one rare scenario where you are getting 0.91, almost closer to 1. Okay, so anything which is in around 70, 60, that is also considered to be good. It all depends upon the data set. It all depends upon your data set. Okay, so we are done with this example. This is where we can end your details. Model accuracy, there is nothing like an accuracy for the regression part. In regression, we measure it by the R square value, mean squared value, RMSE value. For classification, we measure accuracy. For regression, we measure MSE value, RMSE value, and R2 score. So that's about your model performances for the regression. Okay, so R2 score should be as closer as possible to the 1, whereas your RMSE and your MSE is your measure of error. So this should be as low as possible. That's it. Yes, classification I think we'll be able to do. Okay, I'll explain you the logistic regression and then we can take the example straight away. First theory, then practical. So completed everybody? All of you are done? Okay, great then. So hopefully these points we have just discussed, so they are fresh, so you'll be clear about it. Now we can go for our short break. Okay, and let's do the polling activity. If R2 score is less, that means your model is not good. You have to change the values here. Maybe you can change your, you can normalize your data. Okay, and try to put the normalized form of the features. Here it was not required. Okay, maybe in another example I'll show it if the time will allow today, or if not then next week. So you have to basically apply the same thing, your feature, you have to scale your data, and you can also write here in one this, just one more thing you can add here is normalize equals to true. That could you can do normalize equals to true part. This could be sometimes also turn around to be a good part. But you can see that there is no change in the model. Standard scaler, normalization you can do to improve your in this model there is only one thing that you have to change these features. This is a linear regression here, there will be no other changes. You can make proper selections of the features. If the R2 score is not good, that means you have not selected a good feature, maybe you have selected wrong features. So that could be one criteria. So this could be the initial steps will be having your Y might be not normally distributed, so you have to check if it is not, if it is there or not. Then there could be a chance of selecting a data which is having a scenario of a highly correlated value. So that is also could be one criteria to eliminate these. Okay. Intercorrelation between features should not be also high. So many small criteria are there that you have to consider it. Okay. Yes, Ramesh, I'll show it once as I'll proceed with different examples. Okay, please give your valuable feeds in the poll, and the rest things we will discuss after the break. Let's take 17 minutes break today as we have to take second example. So let's take 17 minutes break today. Poll is on. Quickly provide your poll in the chat, and then I'll take the theory and the practical part. Break is for 17 minutes today. Everybody give your valuable feeds in the poll quickly. Hello everybody, welcome back. Hopefully all of you are back here. Let's get started with our okay guys, so here we are with all our data, all our details. That was your end of linear regression. Linear regression could be used here, could use these various parameters that could be used to make the changes, like intercept, fit your intercept which is by default true. Normalize when you wanted to normalize the regression variable before performing. So this is another way of normalization. Okay. These are your only two important attributes. Rest all are not that. These are your two important part, which could try to modify your scikit-learn fit or scikit-learn package. Regression, does the regression variable refer to the target? It depends upon whether you are using it. Variable are generally for features. Next part is our logistic regression. Let's concentrate on this. So the purpose of logistic regression, I think straight away it is writing the equation, so I have to write all these details from the scratch. Only two slides is there, which is not enough. So let me explain you in deep with our whiteboard. So let's talk about that. First, we have to discuss our logistic regression part. So we can straight away take that logistic regression, and let's try to make a fit for this. Logistic regression algorithm. The question arises is that where does we implement it? Where to apply? I'll be sharing these notes with the team, so you'll automatically get them. They might be mailing you all. The next problem is the classification problem. Next is my classification problem. Think about, say for example, we are having three details. We have got user ID. We have got age of a customer, and we are having salary of a customer. A new iPhone is getting launched next month. This is a hypothetical scenario. The manager at the various Apple stores, at an Apple store, wanted to target certain amount of revenue, and in order to do so, they wanted to target some of the esteemed customers, just to increase the total overall revenue at that store. In order to do so, they have gone through all the previous transactions that has ever happened at the Apple store. So depending upon the user ID, let's say user ID 157186, age will be there, 48, salary is, let's say, $41,000. On the purchase side, we have got yes. On the purchase side, we have got yes. So these are all my past transactional data. At Apple Store. Next will be a user ID 1793210, age 35, age is 35, salary is $55,000, and purchase equals to no, 213221, age is 19 years, salary 14,000, no, and 1911, some random number I'm taking. Age is 29, salary is $85,000. Yes. Now on the basis of it, we are having the data. First of all, we have to see our target. The target is purchased in this case. What is the nature of the target here? That will be the deciding factor if it is a regression problem or if it is a classification problem. In this case, purchase is categorical data. Correct? If it is a categorical data, this will mean that you can apply a classification model to it. From all the different list of the classification model, right now we are looking for one of the important algorithm which is called as logistic regression. Name is regression, but it is used for solving any classification problem here. So here is my logistic regression part. Let's try to take its theoretical part first. In case of logistic regression, what does it gives you the output? In linear regression, we were trying to establish a linear relationship between your x and y. Logistic regression actually gives you the output in terms of probability for the given feature as a response. Logistic regression gives output or gives response, gives probability distribution as output. Cumulative function for the given feature x as a response. Point number one. Point number two, logistic regression is actually nothing but it is logistic regression is non-linear. It is non-linear transformation of linear regression. First see the final forms of the equation, then I'll prove this, that how from linear regression we have got a non-linear transformation form of the equation which is called as logistic regression. Here is your outcomes. Okay. You might be thinking that why not let's apply linear regression. What is the problem with the linear regression? So the problem is your responses. See, in this case, our response is straight away either 0 or 1. So either your y will be 0 or your y will be 1. Let us say this is a diabetes. This denotes if a person is having diabetes or not. On the x-axis, we are having body mass index. So when we are trying to compare body mass index compared to your diabetes, you will be having 1 and 0. Compared to above problem statement, we can compare age versus purchased or not, salary versus purchased or not. So that could be this could be one criteria. This is our hypothesis. Now here are my responses this is all our responses here. Remember, this is all about one. Red denotes person is diabetic. Blue color denotes the person is not diabetic. 0 indicates person is diabetic. 1 indicates the person is not diabetic. This is a plot which is a non-linear form, right? This looks like a non-linear plot, right? Linear means this, non-linear means you will get a curve or something. So this is denoting a curve plot. Remember that logistic regression, the working of logistic regression depends upon a function called a sigmoid function, and that sigmoid function gives you an S-shaped distribution. Logistic regression hypothesis depends upon hypothesis equation, of course. Okay, the model equation. You can call this hypothesis equation by the name of your algorithm. So this algorithm equation is given by sigmoid function, and a sigmoid gives probability output for input feature x. Okay, let's write the equation here. How does it look like? Mathematically, it is given by, so this gives you logistic regression uses sigmoid function that gives the probability as a response. Sigmoid function that gives probability distribution. Now, one more thing that you have to keep in your mind while implementing the logistic regression, that our y, we are calculating probability for y equals to 1 for the given x, and this will be given by 1 upon 1 plus e to the power minus e. where z equals to beta naught plus beta 1 into x. Here your z equals to beta naught plus beta 1 into x. Pick your equations. Clear? Probability for, we are calculating here probability for y equals to 1. Probability for y equals to 1 for the given feature x. Fine. Z value is your linear form, and that's how they are connected. This is, you can see that this is your linear regression, right? Z is nothing but this is your linear regression. So you can see that's how your linear regression equation has been transformed into a sigmoid function, which is the core function for your logistic regression. Okay, this is one part of it. Remember that we are only looking for probability equals to success. Y equals to 1 means probability for success for the given value of x. We don't calculate probability for 0, and that's how these distributions, what you see here, these are all distribution. This line denotes the probability for y equals to 1 for the different values of x. In the next line, I'll discuss it better, that how exactly the logistic regression classify itself, classify the data, how logistic regression performs the classification. An easy part here. You take here my body mass index x, got here my y equals to 0, y equals to 1, and now pick my values. These are all coming out to be 0. These are all my zeros. Y equals to 0. On other side, we can take here y equals to 1. Fine. Now let's pick my values here. Remember that this is the outcome from the sigmoid function. Now question arises that these points what you see, what are actually the point over this curve denotes? Each point over this curve denotes probability for the given value of x. For the given value of x, let's say x equals to x naught. Okay. Similarly, x equals to x1. So for every given value of x, what you are getting output or response, each point is probability. As a response for feature x. Okay, and by the way, this is for one class. You will be only getting it that what is the probability for x equals to, for y equals to 1. Only for this we are calculating. We are not calculating it for 0 or we are not calculating it for 1 separately. Only one value you are calculating, and that is probability for y equals to 1. So for each point, we are getting probability response, and this probability is for y equals to 1. Y class. That what is the probability that for x equals to x naught, that this outcome will be 1. Similarly, for feature x equals to x1, what will be the probability for y equals to 1? Now that's how we can use a threshold value to divide these responses. The threshold value will be at 0.5. The threshold value will be at 0.5. Y equals to 1 equals to 1 upon 1 plus e to the power minus z. To place a z value, this is your value, guys. Now remember that if probability for y equals to 1 for the given x, if it is smaller than 0.5, then we'll say my response is, my final output will be 0. Similarly, on one side we have got probability for y equals to 1 for the given x. This should be greater than 0.5 to give you output as 0. Sorry, give you output as 1. So when it exceeds 0 greater than 0.5 for, so likelihood of a probability for the given value of x for y equals to 1, if it is greater than 0.5, we'll say that I'll repeat again, for y equals to 1, for the given value of x, what is the probability for y equals to 1? If it is greater than 0.5, outcome will be 1. Right. Definitely, if for y equals to 1, for the given value of x, the probability is greater than 0.5, that means you can also say that probability for 0 will be smaller than 0.5. I can say that, right? Because probability of y equals to 1 and probability for y equals to 0, both will be combined to give you 1. Now this, similarly, if you will check here, if you get here in this case, if this particular thing happens, it means that automatically what you have to understand that probability for y equals to 0 is greater than 0.5. So definitely our response would be 0. That's how it works. This is how your logistic regression works. Clear? So that's the principle. This is how it will be working. Two responses you will be getting just by the help of a threshold limit, which will be at 0.5. So probability for y equals to 1 for the given value of x, if it is smaller than 0.5, then output is 0. And probability for y equals to 1 for the given value of x, if it is greater than or equals to 0.5, then output or response will be 1. These are your 2 points. So we are calculating only for probability for y equals to 1 part. So this is a bit tricky because usually people don't understand probability much, but hopefully you have understood them. Here we are just looking this as a threshold, and any value which is greater than 0.5, the probability value, if it is greater than 0.5, output will be 1, and if this is smaller than 0.5, then output will be 0. Fine? Okay. Now that we have understood here, this is your equations. So that is the summary part what I said, that in which condition you will be getting 1 and the other condition will be 0. I'm moving to the next part. Any questions till now anybody have? This is the working of your logistic regression. This is the working of your logistic regression model. Now this is the easier one. Now we have to take one more form of this equation. Everybody is clear? Please draw a response fast, guys. You have to take the example as well. Is it clear till here? We're getting here, it is all about working with the probabilities. Yes, if you have enrolled for the machine learning, there you will get the similar type of explanation. I don't think so. There will be more detail in that. But yes, you will be understanding more number of algorithms there and more different varieties of problem statements and more complex problem statements will be discussed in the machine learning batch. So complexity will increase, but explanation will be more or less like this. This was your linear form. This particular part what you see here is a linear form. How about another equation? Sorry, non-linear form. Next is a linear form of logistic regression. Done, everybody? Now let's try to discuss here about. Let us try to discuss in our next part. Okay, linear form part. This is my equation of the linear regression. Y equals to beta naught plus beta 1 into x. What is the nature of the y here? Y is continuous. Y is continuous form here. Okay. Now, in this case, what we have to do here is that we have to pick our data. We have to make changes or modifications on the y side. First change will be pick a odd ratio. Odd ratio will be given by probability of success upon probability of failure. When we say probability, we are trying to compute it for y equals to 1 for the given x. Probability for y equals to 1 for the given x. This ranges from 0 to infinity. This odd ratio thing, we don't pick up probability because probability is up to just 0 and 1 part. We are looking for something which should able to justify our range of the data. So we have taken here Odd ratio is one of the pick that we take. The range of the odd ratio is 0 to infinity. In order to increase its range from minus infinity to plus infinity, this will be not having a range into the minus infinity part. I mean, this will be 0, right? So if this is 0, the maximum value could be on the, so maximum it can go up to 0 on the, and when this will be 1, then maximum value on the positive side will be infinite. That's called as odd ratio or odd probability. One of the same thing, odd probability or odd ratio. Mathematically, we have to take log base e, and then we pick here my probability part. So probability for y equals to 1 for the given feature x upon 1 minus, y equals to 1 for the given x and this is how you create your another form of the equation, okay, which is called as logit form. Logit, the difference between logit form and the sigmoid form is that this does not gives you the output in terms of probability, but it will be giving you a response which is more of a continuous type, and at this will tend to, okay, if I'll just show you in terms of plot, show something like this. So there are two possibilities here. One is that you will be having a class 1. This is your class 1 here. And on the other side, we have got class 0. This is all about my class 0 here. And this is your response. Okay. So here is your slope part. This is your slope. And here is your intercept given by B naught. For the given value of x feature. At minus infinity, the value will be 0. And at plus infinity, we are having our response as 1. So here we go. One side we have got 0, the other side we have got 1. This is your linear form of the logistic regression. Quite an important part, because from here only your sigmoid is drawn. Take this E and put this on the right hand side, and then adjust the settings. What you get here is a sigmoid form which will give you the responses in terms of probability. Okay, done. So two forms are there. Obviously both equations are drawn from each other, but this will be a non-linear form and this will be a linear form representing the same thing, doing the classification stuff. And that's where our theory part of this ends. Now the question arises that if we have got these two parts, there might be something called as an error part as well in this case as well. So how does we measure that? Error in classification. Error in classification is actually given by error function measures misclassification This measures misclassification. What is the function name? Function name is cross entropy. Function name is cross entropy. Okay, next about here. Classification uses entropy. You might have heard about that entropy term in your graduations. What is the role of entropy here is that it measures the degree of randomness. It is used for measuring entropy function that measures degree of randomness or disorder. In short, we are measuring here the misclassification percentage in your data. So we are measuring here what is the percentage of disorder in the data set, the randomness, these are all we are trying to measure. And what is misclassification? It is nothing but if your original class was 0, but your predicted class was 1. Similarly, if your original class was 1, your predicted class was 0. So that is what? That is nothing but this is your disorder in the data set. Could be represented in these red dots or blue dots. So these are all your misclassification. For binary class, okay. So that is what called as your misclassification, and we have to measure it. Fine, and that's how it is. You can see in this case when your samples are across 2 points and we are trying to measure it, these are all your misclassifications. And that is done here. This is all about our examples for the given value of x. Theory part is over, that's it. Simple, let's keep the thing simple here. Okay, this is more of a machine learning topic, correct? So maybe if you have enrolled for that, there you will study more complex problems. Majority of the portion of the logistic regression I have covered here only. All right. Okay, so everybody is clear about it. What are we trying to achieve from the logistic regression is we can compute the probability, and if the probability is wrong, okay, sometimes then there will be that will result into misclassification. What is misclassification? When your actual class is not equal to your predicted class, right? Let's say original class was 0 and predicted class is 1, or vice versa. Fine. To measure this, we use entropy. Fine. So that is a bit of mathematical part which we actually don't need. What we need here is the help of scikit-learn package and this function which we have already explained. Odd ratio I have already discussed. This pi is nothing but this is your probability for 1 for the given value of x. and 1 minus the same value. This is your logarithmic of log odds. This is also called as your log odds, okay, or log of your odd ratio, and which will be given by your the particular value, and we get a linear regression part. See here, it is a linear regression. So two part is there. These are all your equations. This is called as sigmoid, and the other form is called as your linear form. Okay. Now this particular package, which is gonna help us in writing the logistic regression section, has got a plenty of stuff. Okay, and as we'll progress ahead in the equations, in the practical, I'll show them. I'll show all of these. So let's take our second project in your chapter number 8. I think there are 3 algorithms that we can discuss. So your third one will be your unsupervised learning. So in lesson number 8, let's pick our next algorithm. Causal linear regression. For our given algorithm, which is advertisement ad analysis. I'll share these codes. The previous codes I have already shared. I don't know if you have received it now. If you haven't received, please raise a ticket, because from my end I have already shared it. So logistic regression is our next part. In this we will be taking up diabetes classification. Diabetes classification. In this we will be taking up diabetes classification. This is your assignment number 2 or project number 2. Ready, everybody? This is your data set, which is coming up in your screen. Start with your Jupyter notebook. Everybody start with your Jupyter notebook. That is taking so much of time. EMA Indians diabetes data. Okay. And your column names. So this denotes your number of pregnancies. Then we have got your plasma glucose concentration. This is your glucose. This is your blood pressure, 72. The next is your skin thickness. Particularly it is talking about the tricep skin thickness in millimeter. This is your insulin, serum insulin present in the body. Then next is body mass index, BMI. Next is your diabetes pedigree function. Next is your age of the person, and then class 0 or 1. Okay, so I'm just sending you this data set which I'm going to use for my classification, just like the way I have shared it. So wait for I need to upload in my GitHub, and then I'll share it with everybody. Take your data set. Now we have to read the data. Let's get started. Let us get started with our project part. Let us get started with our project part. Project number 2. Let us get started with by adding the data set. First, we have to start with our. So in this case, we will evaluate the diabetes data set and we will try to perform the classification among the data set. So let's get started by first import the data set. Part number 1. Import the data set. Point number 1. Packages will remain as it is. All of these are your packages. I'm just sending it in the chat window. Okay. Try to speed up, guys, okay? I'll take the questions in the end. So for the time being, you can just keep your questions aside. Let's try to cover up this particular example. Let us import the data set. If you wanted to take the data set from the URL link I have provided in the chat, if you wanted to save it in the location so you know how to take it. So let's pick that. Point number 2, take your data set from the given location. We can take here my diabetes, which will be given by pd.read_csv, and we take here my path. While saving the data, you have to ensure that that .txt should not be there, but it should be saved as all files. So it's better you take the URL, otherwise you'll make a mistake. By default, it will try to take the data in .txt format. So you have to ensure that it is not txt, but it is treated as all files. And then you can save it. Now we take here my data with header equals to none. We don't have a header. Then we take here my diabetes data set. Let's pick my 5 observations. First 5 observations here. In fact, I'll just remove it. View first 5 observations. Let's take my diabetes dot head function, and these are all my responses. Next, after taking up all these, after we have imported the data, this was your analyze. Now let us add the names of the column. So we can improve our data set feature names. So let's add a proper header from the names section. Now these names are also available to us. Okay, so let's pick that. I'll just create the names and I'll add it. So let's take a list of names, feature underscore names, which is equals to pregnant, glucose, blood pressure, skin thickness, etc. Instead of pregnant, it should be pregnancies here. Let's just change the names. Pregnancies, glucose, take care of glucose here, blood pressure, skin thickness, insulin, body mass index, diabetes pedigree function, age, and then outcome, or you can call it as label. This is your list of the data. Sorry, list of the column names, feature names, whatever you wanted to call it. This is your feature names. After we have got the feature names, let's add this. So use the feature names and said earlier to fix your headers of the data set. So while reading the data, you have to particularly provide the names. So I'll copy the same thing, the same line, and this will be my data frame, the diabetes data frame. In this case, I have to add here names, which will be equals to your feature names given by your diabetes data frame. And while taking the path, please ensure that you choose your own path. If your URL is working, provide URL. If your names are working, if you have taken the path correctly, then you have to take the path by your own. Better, you can use the URL so that it will not create any issues again. Again, view your first 5 observations. Diabetes underscore data frame. Now all the data is easily observable and we are able to see their headers as well. So this is to verify if your data set is updated by the new headers. You can do it also by the tail function. Next is view the number of observations and features of the data. So particularly we are targeting here to take the shape here. Pick my shape and you will see that it is 768 cross 9, which indicates 768 rows and 9 columns. 768 rows and 9 columns. Again, something new to learn. In this case, once you are over till here, just write done in this. Once you are done till here, drop done in the chat, and then we'll discuss the next part, which will be about how does we can handle the missing values in this case. So finish this all part and write done in the chat. Okay, great. Let's get moving to the next part. The next part will be about how to handle the missing values. You might be saying that where is a missing value? I'll show you how it is hidden. The good thing about the data set is this: handling missing values. In order to handle the missing values, yes, Roshan, you can also do that as well. Okay, handling the missing value. Take your data, is null dot sum. It shows 0. So where is the missing value found? The point is that in this case, the missing values are there, and those are 0. In glucose, blood pressure, skin thickness, insulin, body mass index, and diabetes pedigree function, our values wherever is 0, that is not actually a 0, but it is a missing value. So let's create a dummy data for the time being, diabetes, which will be equals to, from your main data frame, I'll simply drop 2 of the columns. Okay. You can also try to pick your, so let's drop your pregnancies and outcome. The reason is that these two are your, so what are we left with? We are left with these columns. Now pay attention in this case, wherever our 0 is there, let us replace it with np.nan and in place equals to true. Do your missing values, it will show you 0, drop these 2 columns. The reason behind why these 2 columns I have dropped, because pregnancy being 0 is okay. Outcome is definitely will be 0, which means non-diabetic person. So we have to ensure that these 2 columns are not there when I am replacing 0 with a nan. Now let's check what happened. Here is your number of missing values. short underscore values, false. Ascending equals to false, of course. Total number of missing values in insulin is 374. Total number of missing values in your glucose is 5. In age, there is no missing value. In diabetes pedigree function, there is no missing value. Now, these are all my missing values. Once we have done, let us try to replace this. Okay. Method number 1. Target the insulin part. Diabetes. Insulin.unique. These are all your continuous value. Whenever there will be a continuous value which is missing, straight away what you will do is you will replace it by missing. Replace missing value by central tendencies, either mean or it could be median. In this case, I am going to apply replace by mean. Mean of insulin value. So how to calculate the mean of insulin value? Simply use a mean function. Got here 155 point this. I'll take a round of this. The reason is that all these values are just dot and not dot dot dot, something like that. So 156 good works good. These are the method. Why not? Whenever missing values are there, and if it is a numerical data, we replace by the central tendency. For continuous value, it will be replaced by mean and or median. There is no specific reason. I chose it from my own choice. Either you have to use it for mean or use it for median. Okay. Now this next point here will pick my column. Diabetes. Let's target the insulin. Anything could be used here. Replaced by the central tendency is important. That is what you have to remember. Target our NAN, and we will try to target it by, we have to replace these value by the mean. Updated by in place equals to true, and this is done. Okay, so first check your unique value. Okay, remember that mean is generally used for the continuous data. Mean or median will be for continuous data. If it is a discrete, sometimes it could be a possibility that you are having a discrete, sorry, not discrete, categorical one. So in categorical, you will replace it by mode. In categorical, it will be replaced by mode. So for continuous, replace by mean or median. For discrete, definitely for discrete, choose median. And for categorical, it is mode. For categorical, it is mode. So I'm just sending this entire code again. From here, if you have already taken, it is good. Otherwise, you can just match if anything has been missed out. So line number 18, 19, 20, and your last, which is update. Currently, just one column has got updated. After this is updated, your value will be gone. Your missing value will be gone. So we can verify it by using this function again. We can see that your insulin, which was 374, that has been replaced by 0 now. 374, it is now 0. Next, impute method. Next, one more important details that we'll discuss here is imputation method. Imputation method is used to replace the missing value by just one function state per way, and that is called a simple imputer. So method number 2, when you have got, if you have got a lot of columns with a missing value, like in this case 4 columns are having missing entries. So in this type of situation, when you have got lot of column missing, then you better apply a strategy of replace by median or replace by mean. In spite of doing it explicitly, this will become complicated, right? First you will calculate mean, then you will replace it. So is there, and what if we are having a scenario where 20 columns are missing and all those should be replaced by median or mean approach? That's where imputation will be really handy. This is offered to us from the scikit-learn package, from sklearn.impute, import a simple imputer. Take here my imputer part is equals to simple imputer. Take a strategy equals to median. Median is my strategy name. Take my x data, pick my imputer dot fit underscore transform, and then take my diabetes. So you can just pass the diabetes data straight away. You don't have to worry about if it is having a missing value or not. Wherever the missing value will be there, it will automatically scan it, and it will apply the median strategy, mode strategy, depending upon all 3 strategies are there in this. So strategy could be we can have a strategy equals to mean, or it could be median, or it could be most frequent. It could be most frequent. So I'm sending you this function. Start working. Remember where you have to apply this when you are having more columns missing. Otherwise, if you have got 1 or 2 columns missing, better you apply the replace function to replace your data. All things good, but there is one odd part, which is the response of this imputation, that is an array. It will give you output in terms of an array. That means we have to again convert our data into a data frame. Okay, we have to convert our data into data form. So let's get started. Just display your X data. Take your X data here, print it, and put them in a print function. Now let's re-prepare our data set, and we have to again re-add those 2 columns which we have dropped. So prepare your data. Prepare clean data frame. In order to prepare the clean data frame, we have to target here our X data, and we need to convert them into a data frame part. Simply we can typecast it, and let us store it in a data frame number 2. All good. Let us do one more thing here, and that is we have to add those 2 columns which we have dropped. One was pregnancy. Can take it from my previous data, which was diabetes dot pregnancies. Hmm? Okay. Diabetes underscore data frame dot pregnancies. That's your column number one. The second column that we have to add will be your outcome column. If you have got both categorical and continuous data, then obviously while passing the diabetes, you have to restrict your columns. You have to choose which all columns you wanted to apply through the, you wanted to go through the strategies of median, or if you wanted to get the most frequent or mode part. So for that you have to pass the different column. So this needs to be controlled. Here I passed all the value because I know that every data was numerical, and I wanted to replace it by median. Clear? Okay. Now our data is completely ready, and we are ready to move ahead. Let me send you this particular part now. Start working, everybody. Your data is clean. So this is a new thing. I think earlier we didn't talk about much about this. Once we have got this, we can go back to our machine learning part. We have to find the responses of the dataset. Step number 4. I think it will be step number 5 because step number 4 was handling the missing value. But in the project, there is nothing where it was talking about handling the missing. But definitely we have to do it. The dataset was not clean. Now select the features from the dataset. Same. This will be exactly the same thing which we have already did. That means we have to prepare our X feature, and we have to take our label. Again same 75 is to 25 ratio. Okay, let's get started. To build the model, select the features from the dataset. Pick your X feature, which will be given by diabetes underscore data frame 2. In this case, we have to take everything apart from the last column. This is my X feature. We took here all my data. Okay, X feature done. Next is my create your response target. Feature object is ready. Y underscore target. This will be given by diabetes data frame 2, and pick your column which is outcome. Display your Y underscore target dot shape. Sorry, dot head. So we have got here my features, and we have also got my target. Now that we have got our target and features, let us try to take the shapes now. View the shape of the feature object. You can take here my X feature part dot shape. Similarly, view the shape of the target object. and take here my y underscore target dot shape. Once we have taken my x shape, okay, now train my model. Use training and testing data set to train the model. Split the data just like the way we did earlier. So majority of the thing will remain common, okay? After you have cleaned the data, it's all about you can straight away use it. So I'm gonna use the same thing. Okay, the test size, random state, which is 0, and we have taken our x feature and y target. Let us apply it. Split your data. Now let's create a model. Once we have splitted the data, there is one more thing we can do in this case, and that is we can convert our x train and my x test part, in spite of that, straight away using it. Why not let's convert them into scaling part, right? That will be also covering up your one of the topic. The standard scalar we can use min-max scalar, sorry. And that will be a good idea that our model will be normalized. If you wanted to add correlation, you can add correlation, it is up to you. That's totally optional here because in this case, all our data, okay, by the way, one more thing. Do we have any ID type of thing in this case? No. So basically in this case, if you wanted to apply the correlation, you can apply the correlation part, but it is not important because this is a classification example, so you might not get a good response. Correlation works better with when your outcome is continuous. Yeah, I was saying something here related to the min-max scalar. So let's apply that. It will be more of like scaling the data. So I'll just add that additional part. Again, this will be an additional section. So once we have got our features and target, let us try to normalize these features. Let us try to normalize these features. So normalizing, this will be before we split. Just make a correction. Normalizing the features by min-max scalar. Pick your function from sklearn dot preprocessing import min-max scalar. Now pick my scalar which will be equals to min-max scalar. Can take here my feature range. In this case, the more general range is 0.0 to 1. So more or less it will remain as it is. You will take your scalar function and you'll fit and transform. Fit means train and transform means make changes. So first you will apply to your, okay, wait a second. This should be below than this, right? Yeah. First you will apply to your train data set. First you will apply to the train data set. And the response you can save it in xtrain scalar. Next, xtest scalar. This will be given by, now for the next time you don't have to fit it, you have to simply transform it. Okay, so that's where exactly your normalization of the min-max features will be there, which is min-max scalar. This is to scale down your data, the varieties of the range of xtrain and xtest. Like if you will see the xtrain part, it had different varieties, right? Few of the values were there in the range of hundreds, few of them were in tens, few of them were in decimals, okay, and few of them were just unit. So when you are having varieties of range, we have to scale down these. That's called as your normalization. Sorry, that is called as your scaling your data, scaling your features, in fact. So we have to normalize these values in same range. Let's say all these features which were in different range of having different magnitudes, now they will be all in one range, that is between 0 and 1. Okay. It is not both you can do. Either you first split and then you apply this, or you first apply this and then split your data. It doesn't matter. Both does not impact your outcome. It will remain unchanged. Main reason behind the applying these scaling method is always been when you are having the different range of the data. In this case, in this example, even if you will not apply these scaling features, there is hardly any impact in the outcome. And the reason is these values mostly are in same range, 100 to tens, most of them are getting covered apart from pregnancy, which is obviously a single digit response. Okay. When you will be having some values in 10,000, the other value in 1,000, and then you are comparing other feature with your decimal values, that's where the impact will be seen of, if you will not do the feature scaling, then your responses will be biased toward a particular feature. Okay, we are done with this. Our xtest and xtrain, our data is scaled. Now create a model and predict the diabetes outcome. Now let's create our model and fit our data set. Yes, it will be an array. Now I'm going for my default settings. I'm not changing anything here. Logarithmic regression is there. I'll take here my log reg. Pick here my fit, xtrain, scalar, ytrain. Okay. Fitted. Now I have taken all the default settings. There are many other modifications you can do. For them, I'll show you the list of the details. You can try to make changes and adjustments. Okay. Once we have taken all the default settings, let's try to make predictions just like the way we made predictions earlier. So create your logistic regression and make predictions for the given y-test. In order to make prediction, you will take your logistic regression. This is your training part. Fit means train and predict means make predictions. The predictions you can take it in terms of probability as well or log of probability as well. Okay, as you know, the outcome will be based upon the prediction part. Now let's compare this with xtest, scalar, and here are your responses, zeros and ones. All right. Now we have to definitely measure the accuracy part. Let's check for the accuracy of the model. Let's check for the accuracy of the model. So evaluate the accuracy of your model. And how does we evaluate it? We can simply pick logistic regression dot score, compare your y test versus, oh, we have to save this in y predicted value, correct? Wait a second, huh? This has to be changed, y predicted. So we have to compare the y test and y predicted score. Just a second. These are all my predicted response. Y test versus, okay, wait. How could be a different? Reshape the data using if your data is single feature, it contains single output. Expected 2D. It is okay only, it should be array. What is Y test? Y test is oh wait, I got it. Here I have to pass X test. 100% accuracy? Wait, no. Y test. Okay. Oh, 76.5. Okay. Score is about this. You have to, so basically you have to pass X test scorer, which is X test scalar, which will be particularly giving you the value or responses. Let me reshare you this particular code because otherwise you will not have the white thread. So first of all, take your Y pred, then compare it with a score. Remember that in the score part, this is gonna respond the Y pred, and then we are comparing it with the Y test. So this is Y pred part, and this is your Y test. Yes, that's correct. We have compared here the Y predicted and the Y test, actual versus predicted, which is coming out to be 76.25. Okay, now let's make some changes. Accuracy till accuracy, everybody finish. And if you wanted to make some adjustment, no, this is correct only. This takes X test. Whatever is written, it is correct. Okay, please execute everybody. This is gonna return you the predicted value, and this is your Y test value. We have got our response, and we should be getting here 70. The accuracy is 76.5%. The accuracy score is 76.5%. Now let's try to compare the actual versus predicted part for the first 30 responses. If you wanted to check it. So side by side you can compare. So here are your responses. We have got one false result here. We have got one false misclassification. Wrong predictions are here. One wrong predictions are here. So mostly the wrong prediction is on the 0 side. So original value score function takes x test part which will return you the y predicted value. So it is gonna take the x test and it will return you the predicted outcome from here. Okay, so that's it. This is all about our responses, and that's the end of our today's session as well. Okay, we are done here. Now, suppose you wanted to make some modifications here, you can make modifications in this part. I'll just give you the original function, so do read that from the sklearn, and that will be helping you to study more about it. Do a study this to in order to increase the accuracy of the model. Study about this entire thing. What is the penalty? What are the different C values you can increase? Maximum iterations you can increase. You can choose different solver options. By default, the solver is LBFGS, and you can change your random state. These modifications you can take if it is a multi-class classification. So how does you can make sure that your logistic regression can solve a multi-class? Maximum iterations you can increase. So I'll try to make certain modifications. Please watch. First of all, I'll change my by default solver was LBFGS, which I'll change it to liblinear. Liblinear is good for binary class classification. I'll increase my maximum iteration to a higher value 1e9. It means 10 to the power 9. For C value, I am taking also a very high value 0. I can take a smaller value 0.01. Penalty. Whenever you are using liblinear as a solver, penalty will be L1. It has reduced the accuracy, so I think the default settings were much more better. Let me change the C value 1E7. Let's see now response. It is coming out to be 77. So that's why liblinear is there. By default, the solver was LBFGS. So there is only one change that I have made. If you wanted to go through these changes, you can re-update the code of line number of your model creation, re-execute everything, and then you will be able to see the accuracy getting slightly better. I think one response got better here, nothing much. So this is the maximum you can get. Further more changes if you wanted to make, you can read about these. I'll really suggest please choose these hyperparameters and make these changes. Do read it in your spare time. Similarly, I'll suggest you to read about the linear regression. But linear regression is is already a simple one. I mean, there we don't have multiple hyperparameters. But logistic regression, we have to choose different hyperparameters, especially when you're solving a multi-class classification part. So that's you have to take different options there. Make the changes, make the adjustments, and increase the accuracy. So that's it. This is all about our today's lecture. Thank you so much for joining today's session, everybody. Hopefully, you have understood all these points that we have applied to our various data set. Furthermore, in our next week, the first day will be dedicated to take one more algorithm, which will be k-means clustering for unsupervised learning, and we'll also take NLP part, natural language processing. Okay, and yeah, these are all our part here. I have sent it from my side. I don't know if you have not received it. Please, you can generate some. You can contact the team so that they can send you these particular part. I'm not aware about the status. So project submission date will be your think 20 days, 15 days you can consider 15 days post our session finishes. So I think our final date will be on 9th of July. So on that day I will discuss the project as well, maybe in the end, and you can consider 15 days after that. So that makes it, I think, 23rd or 24th here. 24th, right? So it should be submitted before 24th. Any more questions? Adya, over to you. Thank you so much, everybody. Good night. Take care. Do provide your valuable feedbacks as soon as you end the meeting. You will be redirected to an external site. Follow the instructions, give your feeds, and enjoy your rest of the week. Do revise the things that we have covered so that we have so that you will be all updated. All right. Thank you, everybody. Hopefully, I've had an enjoyable session today and this week. These were quite an important and interesting topic. How to apply the machine learning. That's your ultimate use case of the data science. Bye bye, everybody. Thank you so much for your wonderful feeds and wonderful participation. Good night, everybody.